I work as a solution provider with Furnace Improvements. Our company is in the business of revamping fired heaters. We revamp your fired heaters to the highest capacity, longest run length, and highest efficiency. The webinar today is born out of our experience and dealing with customers for more than 40 years. This is our third webinar and I welcome you all. As you are all aware, the whole world is experiencing the COVID pandemic these days. I hope all of you are keeping safe and following all necessary precautions. We'll be talking today about how to get rid of high tube metal temperatures and hotspots in fired heaters using our inclined firing technology. We'll be talking about fired heaters for an hour. Fired heaters, as you all know, are one of the largest equipment in the refineries and chemical plants. It is very easy to overfire any fired heater, almost like a balloon. Fired heaters are very sensitive to burner flames, and you all know about the hotspots formation of tubes. I hope that by the end of this webinar, when you go back to your units, you would be in a better position to evaluate the performance of your fired heaters. Learning is a continuous process. We have learned so much in the past 1 month while preparing for this webinar. So please don't hesitate to ask me a question. Please feel free to share your experience with us. We are going to conduct this webinar today through PowerPoint presentation. We will have the presentation for 50 minutes and then question and answer session for the last 10 minutes. We have been able to improve our webinar based on your feedback. So I request all of you to complete the survey before you leave and send it to us. I will start the session today with a brief introduction of myself. I am a chemical engineer. I passed out from IIT Kanpur in 1974. Since 1976, I've been working on fired heaters and combustion systems. I have worked in KT India, Engineers India, and KTI Corporation. Since 1996, I've been working with Furnace Improvements, fixing heaters for the past 24 years. So I want to start this webinar by thanking our team in the US and India, who have been working very hard for the past 4 weeks. Our team of process, mechanical, and CFD engineers have been working and putting together this presentation. Our admin team has been trying to reach out to all the clients. I am just the presenter today. I'm really happy. We have more than 70 participants registered for this webinar. So we want to make sure before we start our webinar that everybody has been able to log in to the webinar correctly. You will see a control panel on your screen. You should be able to select the sound audio input either through the phone or through the computer. And then there is a question box at the bottom. You should be able to type the question in the question box and send it to us. There is an orange arrow on the top and you can minimize the control panel on your screen by hitting the top red arrow. We will make the webinar recording available to you in case you are not able to sit through that session or you miss any part of the presentation. If you are not able to hear me clearly or has a display issue, please send us a message and my colleague Amreen will be able to take care of the problem. Before we start, I want to give you a brief introduction of our company. Furnace Improvements was started in 1996. We will be completing 25 years in March 2021. We currently have 3 offices. The head office is in Sugar Land, Texas. We have an engineering office in Noida, India. It was started in 2005. We have almost 35 engineers in that office. They are doing process, mechanical, structural, design, drafting, everything. We are a full service heater company. We execute projects on a turnkey basis, including erection. Our CFD office was started in 2014. It is in Pune, India. Our CFD team has been working exclusively on combustion, heat transfer, and fluid flow problems. Our mission has been working on improving the performance of existing fired heaters, and more than 90% of our business in the past 20 years has been breathing new life in old fired heaters. Each heater is custom designed and unique. The problems being faced by the client are also different in each case. We have developed a very systematic approach to solving heater problems. We have also challenged the conventional approach being followed in the design of fired heaters. And today we are going to talk about one such approach where we challenge the concept of vertical firing in fired heaters and developed inclined firing. So, as I said, we carry out process engineering, CFD modeling, mechanical design, structural design, 3D modeling of fired heaters. You will see a list of our valuable clients. If your company is not there, we want to add it in our next presentation. I want to take this opportunity to thank all our clients for trusting us and installing our technologies. The technology we are talking today was first installed in 2010 in 2 heaters at Delek Refinery in Texas. They had 2 heaters and they were looking to install ultra low NOx burners. They came and said, we need another 10% extra capacity. The heater designs were very, very tight. We reviewed it and we told them we could give them 10% capacity increase by installing burners in an inclined fashion. The good thing about inclined firing is when you install the burners in inclined manner, you don't pay anything extra. We are still using the same burners, the same heater floor. All we are doing is inclining it a little bit and installing the low NOx burners. So these 2 heaters are one of the best heaters at Delek Refinery in Texas even today. So our agenda today will be talking about fired heaters, talking about the importance of tube metal temperature, the salient features of inclined firing. We will present a case study and then we will have a question and answer session at the end of the presentation. Let me take this opportunity to explain how we developed inclined firing technology. It goes back to 2005. We had a client in Texas. They had a crude and vacuum heater in one of their crude units. They were looking to increase the capacity of their heaters by 25%. They were working with an EPC company which was involved in the project, and they looked at the heaters and they said these heaters have already been revamped once. The capacity has already been increased. So this heater cannot be revamped any further. And I think it will be best to put new heaters for the extra heat duty. So the project and the client agreed and they started working on new heaters. But within a couple of months, they ran into a problem. And the problem was there was no space available to install new heaters in that unit. So the client came to us and said, is there a way to increase the capacity of these heaters by another 25%? We said we need to study it and we will find out if there is any possibility of increasing the capacity. So we looked at the heater, carried out engineering study, looked at the operating conditions, and then developed proposed revamp scenarios. And then we came back to them with 2 technologies at the same time. We said your heater design is very, very tight. We need to put the burners at an angle. That will allow us to increase the firing rate even further. And the second thing we told them was that we want to inject about 30% flue gas in the radiant section. And by injecting flue gas in the radiant section, what we are doing is we are transferring the heat from the radiant to the convection. It is very difficult to add surface in the radiant section, but it is very easy to add surface in the convection section. So we said when we can shift whatever extra duty you need to the convection section, and we can increase the capacity by 25%. The client liked our idea. We went into phase 2. We did a fair amount of engineering, but suddenly the project got cancelled because the project cost got too high and the crude prices crashed, so the project was cancelled. But we were excited about these two developments. We decided to move ahead and install it in other heaters. So this is how we developed this simple inclined firing technology. I want to talk to you a little bit about how heat is transferred to fluids in fire heaters. Very, very simple. We have a sketch here showing the radiant section. We have a refractory lined wall. Then we are showing tubes, and we are showing a burner flame. So in heaters, you will see that there are two modes of radiative heat transfer. There is a direct mode of radiation heat transfer, which is radiating to the front half of the tube, and that is the predominant mode. And then we have the re-radiation, which is the radiation coming back from the refractory to the back side of the tube, and that is the re-radiation. And that also contributes a significant portion of the radiation. So these are the two radiant mechanisms, and mostly it is the hot flue gases, the carbon dioxide and water vapors, and the hot temperature is what are the gases which are doing the radiation. The flame never comes into the picture. So the second mode is the convective heat transfer, and about 15% of the heat in the radiant section is transferred by convective movement of hot flue gases around the tubes. And once the heat is transferred to the tube from radiation and convection, now the task is to transfer the heat from the outside of the tube to the inside of the tube. And this is where things get a little complicated, and that's what we want to talk about today. If everything is good, the heat will be transferred from the outside of the tubes to the inside of the tube. But there are two things which can happen, and those two things are either you can have a scale on the outside, or you can have coke layer on the inside of the tube. And either of the two things will start impeding on the heat transfer because they are not good conductors of heat, and they will cause problems. So what we find is it's mostly the flame impingement or hot flue gases leading to formation of scale or formation of coke on the inside. But both the things are not good. And once the heat is transferred to the inside of the tube, then it is the film, the thin fluid film, which takes the heat from the metal wall or the coke and then transfer it to the bulk of the fluid. And that is the convection mode, which is transferred in. So basically, if you see, even though we call it the radiant section, all three modes of heat transfer are there, which are taking place: radiation, convection, and conduction. And in steady state, everything has to work this correctly. I'm not trying to scare you with the equations, but the basic equation we are going to be talking today was developed by Lobo and Evans, two great engineers, back in 1939. That is how far we go, and they are still holding good. Every heater company uses the same equations. And here, I want to draw your attention to only two parameters. One is TG over here, if you see, and TT. TG is the absolute temperature of the flue gas, and Tt is the absolute temperature of the tube or the tube metal temperature. And the first component is radiation component, which is predominant component, and it's nothing but Stephen-Boltzmann equation. And the second component is the convection component, which is 15%. So here we want to tell you that to transfer the heat, we are using fuel gas and burning it with combustion air. And when the combustion takes place, the temperature produced, the flame temperature produced is in excess of 3000 degrees. And if we are using preheated air, it will be even hotter. So the power of flame is immense, and it is best to keep the high temperature flue gases away from the tubes. No material can withstand these temperatures. So in nutshell, simple theory is if you have flame touching the tube, you can call it a problem or disaster. And our basic rule is keep the flames away from the tubes as much as possible. The second parameter we are talking over here is the tube metal temperature. And this is what we are trying to control. So tube metal temperature is the external temperature of the tubes in the radiant section. It varies in the radiant section. In order to have the best heat transfer possible, you want to keep the tube metal temperature as low as possible. So the lowest the tube metal temperature, more better will be the heat, And since we are having coking service or hydrocarbon fluids inside the tube, we have clean tubes at the start of the run, and as slowly the coke forms, the tube metal temperature starts going up. And tube metal temperature, as I will explain to you in a minute, is nothing but a sum of bulk fluid temperature, temperature rise across the film, coke, and metal. I am not talking about the scale. And the thumb rule is the clean tube metal temperature should be bulk fluid temperature plus 100 degrees. That's how low the clean tube metal temperature can be if everything is right. So the tube metal temperature calculations basically talks about three components, as I said. Temperature rise across the film, temperature rise across the coke layer, and temperature rise across the metal layer. And then you add all these temperature rise to the bulk fluid temperature, and you will get your tube metal temperature. The sketch we are showing you here shows you a TMT rise, and you can see that most of the temperature rise is taking place across the coke layer. The temperature rise across the metal and the temperature rise across the film is very, very low. For those of you who are interested in calculating, I'm just giving you the formulas. I just want to show you how the tube metal temperature calculations take place. Very, very simple. The first term in all the three equations is nothing but the flux, Q by A0. So you can add, you can either use average heat flux or you can use maximum heat flux, depending on what you want to calculate. You want to calculate the average tube metal temperature, or you want to calculate the maximum tube metal temperature. The maximum heat flux is typically 1.8 times the average heat flux for single fire heaters. So, and the last term in all the three equations is nothing but the diameter correction. I mean, you can even neglect it if you just want to do an approximate, So the film temperature is dependent on the heat transfer coefficient. The coke layer is dependent on the thickness of coke and the thermal conductivity of the coke. And the metal temperature rise is dependent on the metal wall thickness and the thermal conductivity of the metal. All these equations are available in API 530 standard. So they are very well established equations. So why do we experience high tube metal temperatures? And our analysis says most of the high tube metal temperatures and hotspots are caused by flame impingement. It is also a result of overfiring, as it could lead to large flames. Flame impingement may not be easily visible, and it could be these hotspots could be due to high flue gas temperatures in the vicinity of tubes. Tube skin thermocouples are very good indicators of high tube metal temperatures, but they only provide you with a point measurement. Infrared surveys have become a lot more common, and they can provide a complete picture of the radiant section tubes. There are two major reasons for high tube metal temperature. You can either have scales on the outside that could be causing problems, or coke inside the tube that could be leading to high tube metal temperature. Metal oxides are not good conductor of heat and can lead to an increase in metal temperature of anywhere between 50 to 100 degrees Fahrenheit. Similarly, the coke formation on inside the tubes can lead to a temperature rise anywhere between 50 to 200 degrees. So if you have a crude heater operating with a 650 degree outlet temperature and your tube metal temperature is 1050, you can start thinking about that extra 300 degree increase is coming either from scale or from coke. That's basically what is happening. So coke buildup or external scales, that could be the two reasons. Let us look at the coke. If you see the metals have thermal conductivity anywhere between 200 to 300 BTUs per inch. And coke, depending on whether it is fluffy coke or whether it is hard dense coke, the thermal conductivity can vary between 1 to 30. We typically use 15 in refinery applications. So the coke has 10 times lower thermal conductivity or 10 times the insulation value. So if the metal temperature rises 25 degrees, the temperature rise across the same thickness of coke will be 10 times or 250 degrees. The thumb rule is 1/8 of an inch of a coke adds up to 100 degrees of tube metal temperature rise. This is a picture of coker heater, and if you look closely, you can see the scales on the tubes. That's how bad the situation was. This is the double fired heater. I don't have to tell you what happens when coking starts, but coking of tubes will lead to several problems in fire heaters. Tube metal temperature starts going up. Fluid side pressure drop also starts increasing. Firebox temperature goes up. To maintain the same heat transfer, the firing rate goes up, the efficiency comes down, and ultimately the charge rate starts limiting. And finally, you have to shut down the heater and either decoke it or peg it to clean the tube and then start all over again. And that's a very expensive shutdown if you have to do it. So here we are showing you a radiant tube metal temperature profile. And even though the model we use for our calculations is based on continuous stirred tank reactor, that means the flue gas temperature across the whole heater is uniform. There is only one temperature, but that does not happen actually in real life. So you can see in a case of a vertical cylindrical heater, you can see the hotspots over here. You can see these hotspots, and the temperature is almost like 1130, 1150 degrees, so you can see this hotspots. Similarly, this is another depiction of radiant heat flux in a vertical cylindrical heater. We are trying for uniform heat transfer and uniform heat flux in all the radiant section, but the reality is much different. The presence of ultra low NOx burners and long flames have created zones of high and low temperatures. The industry has also moved to long, narrow boxes to save money, and that creates a temperature gradient in the firebox. And this gives us a very different flux profile. Our experience is that flames remain straight for only 10 to 15 feet. They are just gas jet, and afterward they start losing shapes. The flames are drifted towards the tubes, causing high tube metal temperatures. And in this slide, you will see the flux variation actually, and you will see the flux variation in the whole length of the tube. The top 1/3 is only 7,000, the middle 1/3 is 15,000, and the bottom 1/3 is 22,000, almost 3 times what is happening on the top, and the average is around 13,500. So you could see how much flux variation we can have. And you can also see the maximum heat flux going almost like 37,000. And this will definitely lead to coking and high tube metal temperatures in fired heaters. So I did some research, and I looked at API 560, I looked at API 535, and I looked at what type of solutions are available if you have high tube metal temperatures. And I found that there is no permanent solution available. They are all telling about change the burner tip or check the burner tip angle, check the burner tip location, or if your tip is plugged, So poor mixing of fuel and air, flue gas recirculation pattern. So I could not find any real fix to solve the high tube metal temperatures in fired heaters. So these are all temporary fixes, and our experience is once you start having high tube metal temperatures, then it is not a question of when, but how. It's not a question of what needs to be done, but when will you have a shutdown, and how long can you avoid it. So our technology is very, very simple. The basic premise is high tube metal temperature is the biggest problem in fired heaters. And most of the high tube metal temperature is due to localized flame impingement. Hot flue gases in the vicinity of tubes causes high tube metal temperature. Historically, fired heaters have been fired vertically upright, sideways, downwards. Our technology installs burner at a slight angle and reorients the burner flame away from the tube. It is based on a very simple concept, moving the flames away from the tubes. And when you talk of radiation heat transfer, the flames never come into the design or heat transfer. So by moving the flames away, we are not affecting the overall heat transfer. And in fact, we are moving towards uniform heat transfer. And this slide I'm showing you, you can see we have looked at the temperature profiles, and you can see the flames are in the center and rest is lot cooler zones all around the tubes, And that's what you want actually. You want hot flue gases in the center, radiating heat to the tubes and having uniform heat transfer. So our technology is eminently suitable for existing heaters with ultra low NOx burners. We have seen that these heaters were originally designed with standard burners. When the standard burners were replaced with ultra low NOx burners, the heater started having hot spots and flame impingement. In most cases, the burner to tube clearance reduced, causing problems in operation. And it is not possible to enlarge the radiant section to keep flames of the burners away from the tube as possible. And we have overcome this limitation without increasing the cost of the heater, without changing the design of the heater, to put these burners at a slight angle of about 5 to 7 degrees. Most of the time, you won't even notice it. So flames of the burners, ultra low NOx burners, could be anywhere between 15 to 25 foot long. They could be even taller. So when we incline these burners, these flames start moving away from the tubes, and we increase the clearance between the burner edge, flame edge, and the tube almost like 1 feet for every 10 feet of flame length. And if it's a 25-foot flame length, we have added another 2.5 foot clearance between the burner flame edge and the tube, and that's very, very important. Also, we need to remember that flames are not uniform. They are widest at about 1/3 the height. The flame temperature profile is also varying. So in inclined firing, we may have burners close to the tubes, but the flames are moving away. And it's a very economical solution to eliminate flame impingement and reduce tube metal temperature. So in inclined firing, the burners are installed, maintaining enough distance between the burners to allow for flue gas recirculation. We do extensive CFD modeling to ensure that all flames are separate and they are not merging together. There have been some people who think that flames coalesce, but we have done more than 15 heaters and we have not had a single case. We make sure that extensive CFD modeling is done and enough care is taken care to ensure that flames are straight and separate. So we have not had any cases of any flames coalescing taking place in any heater. I want to show you a burner to tube clearance on a 8-burner system. And if you look at this chart table, you will see at 0 elevation or at the floor, the burner to tube clearance is 6 foot 4 inches. But as we keep on going up, and if the flame is 25 foot long, we have added another 3 feet clearance. So what we are basically trying to do is trying to keep the flames away from the tubes, and it really, really helps. And also the flames are not hot at the bottom. They are generally at 1/3 or 2/3 height. That's where they are more high temperature. So it really helps to keep the flames away from the tube. This is at 7-degree angle. This is a picture of a vertical heater, just a graphical representation, and you can see the clearance between the burner and tube in the vertical fashion is about 2.5 feet, and which we increase it to 5 feet. So another 2 feet we are buying, So that's basically what our technology does, just move the flame away from this thing. This is another one in a platformer heater. You can use it, and it's not just limited to VC heaters. You can use it in CRU. Here we are showing the 2 cells of catalytic reformer or platformer heater, which were big, and we can use burners in inclined fashion firing towards the center and moving the flames away. Very simple concept. Double-fired coker heaters have become very common in the industry. We find many are suffering from high tube metal temperatures from day one. The high tube metal temperatures have been caused by long burner flames and inadequate burner to tube clearance. We did a study for a client on their double-fired heater and found that the burner flames were almost touching the tube, or almost like 6 inches away. And we modeled the same burners at 5 to 7-degree angle, and we were able to see a big difference in tube metal temperatures. And the flames basically move away from the tube and start hugging the refractory. We increase the clearance almost by another 2 feet, and the TMTs come down by more than 100 degrees, which is a big number for a coker heater. And this firing pattern can be also used in new poker heaters without any extra significant cost. So very, very suitable. And you can see the flames over here. This is an actual study we did for one of our clients. This is another heater we have done for horizontal tube end wall fired heaters. We don't build too many end wall fired heaters, but it's an old crude heater with end wall fired burners. The heater was experiencing high tube metal temperatures, and we did the CFD to show, and you can see yourself the color of the flames. Red is basically, much concentrated in the center actually, and the tubes are experiencing a lot lower. We even did it in ethylene crackers actually. We did a modest CFD model of a furnace, and you can see the difference in a vertical firing and inclined firing. You can see in our model, the flue gas temperature is a lot lower, and as compared to almost like 100 to 150 degrees lower, and the tube metal temperatures are also lower, and the flames are firing a lot more towards the wall actually. So it can even be done in ethylene crackers if the high tube metal temperatures are an issue. And I know ethylene crackers have a big issue with tube metal temperatures. So today we are going to be talking about a case study on a crude heater. And this is a case which I first told you about when we started. So we got a second chance to look at in 2014 to look at that heater again. The client had gone ahead and replaced the existing burners with new Ultra Low NOx burners and air plenums in 2011. Now, even after doing that revamp, they were still having lots of issues in the crude heater. So they contacted us in 2014, and we did the study and later on the project. So this was a vertical cylindrical balanced draft heater with common air feeding system. The heater was originally built in 1976 and revamped in 2000 and again in 2011. And client was facing a number of problems, was facing capacity limitation due to high tube metal temperatures. The situation was so bad that they had wrapped some of the radiant tubes in ceramic fiber blanket. They were having flame impingement, and it was leading to soft coke deposition in radiant tubes. The client had other issues like combustion air maldistribution across burners. The client could not get full capacity. So we did an engineering study to improve the reliability of existing crude heater, improve performance of existing burners, mitigate flame impingement. They wanted us to restore the capacity of the heater. The heater was firing, facing combustion air shortage during the natural draft operation. So we looked at several ways of improving the heater reliability. So this is the heater design, original heater design and existing heater design. Original was 133, and they had already expanded the heater to 162. The charge rate they had increased from 50,000 barrels to 80,000 barrels. The number of fluid passes they had changed from 4 to 8. The flux had increased from 12,000 to almost like 14,000. What they did on burner side was the original heater had 8 burners of 22 million BTUs each at 8-foot BCD, and they had changed to 12 burners, 16 million BTUs each. When they did that, they had to increase the burner circle diameter because these were ultra low NOx burners. So they went to almost like 11 foot 8 inches, or an increase of 45%. And as a result, the burner to tube clearance was lower by about 2 feet. And this was not even meeting API. So this heater, they gave us operating data for this heater. And let's look at the tube metal temperatures. They were exceeding 1100 and sometimes even 1200. And if you look at it, we analyzed 4 years worth of operating data when they started. If you see over here, the temperature is close to about 800 at the start, and as you keep on going up, it goes up to about 1100 degrees. Then again they clean the heater, it comes down to about 700 degrees or so, 800, and then again it goes up to 1100 degrees within a span of 1 year. Again they clean it. So it was becoming a big problem for them. You expect crude heaters to be running for at least 5 years. I mean, if you have to shut down the heater in 1 year, it's going to be causing a lot of profit loss. So the high tube metal temperatures were really, really acute. We carried out the CFD model of the existing burners and tried to understand what the problem is, and then we kind of worked on the solutions. So the client had 3 major shutdowns in September 2010, July 2011, and January 2014. They were not able to get outlet temperature of 700 degrees. It was running 57 degree lower. The maximum tube metal temperature was exceeding the design value by almost 150 degrees, so they were almost reaching. They were at the maximum allowable tube metal temperature. The heater operation was severely limited, That's basically what was the situation in this crude heater. So this crude heater was a vertical cylindrical heater with 22-foot tube circle diameter and 62-foot height. Burners were installed at 11-foot 8 inches burner circle diameter. The burner to tube clearance should be 5-foot 6 inch, and they were only having 5 foot. And when we started looking at it, we said we would like to change your existing burners and put them at an angle. So we went in with new ultra low NOx burners and did the CFD modeling at a lower burner circle diameter to increase the clearance from the burner to tube, at least meet API 560. So we analyzed the problem and kind of recommended these simple solutions. The first was how to solve the flame impingement problem. So we said we will put new burners on tighter BCD, use inclined firing, and we will use CFD to optimize the BCD as well as the inclination. So we ended up doing about 6 iterations of different angles and different BCDs to arrive at the best combination. We looked at the plenum and we redesigned the plenum, simplified it, and made sure that all the burners are getting equal amount of air using CFD. Then they were having limitations on natural draft, so we put fresh air doors, redesigned and relocated. And they were having combustion air limitations, so we recommended them to put a new FD fan, of a higher air capacity. So that's basically the modifications which we did for them. And our inclined firing is, we came up with 10-foot 3-inch burner circle diameter, and you can see we installed burners at 7-degree angle. We started with 5-foot 8-inch clearance, which is little more than API 560, and by the time we went to 25-foot flame, which was what the burner vendor had promised the flame length to be, we were at additional 3 feet. So 8-foot 9-inch clearance is what we created for them, So we were able to create, and even between the burners, we were able to create a big gap, So I want to show you now some slides of CFD model. We did extensive CFD modeling to come out with the optimum BCD and burner angle. The existing configuration, if you see, had a big flue gas recirculation taking place in the center. If you see over here, this was the flue gas recirculation pattern taking place, and it was pushing the flue gases down straight into the tube. That's what was happening. So that was basically causing the high tube metal temperatures or hotspots in the display. And if you look at our design, in inclined firing, basically there was no such recirculation pattern forming, and it was forming much above, in the upper 1/3. So that's basically, you can see side to side. Now the important thing is flue gas temperatures, and here you see the hot flue gases going directly into the tubes. You can see over here, this is where the flue gas temperatures are impinging. A hot flue gas temperature almost like 2200 degrees. And if you see our design, it's much different. You have much cooler flue gases going into the tubes. The hot flue gases are concentrated in the center. And also, if you see in the existing design, the top half of this thing had very low temperatures. And if you see over here, we tried to make it a lot more uniform. So that was another major improvement we did by putting burners at an inclined fashion. The good thing with CFD is once your model is built and simulation completed, we can study the flue gas patterns, temperature, CO concentration at any cross section, horizontal or vertical. We compared flue gas temperature profiles every 5-foot elevation. At 5 foot, you can see compare side by side. And when you compare at 10 foot, you will see that the hot flue gases are in the tubes. Actually, if you see over here, this is basically, you see the high temperatures, and if you compare this, there's a total difference, stark difference between the two configurations. So we did this at 15 foot, also in 20 foot. And here you will see something very strange happening. You will see the cold flue gases is in the center and hot flue gases are outside actually. If you see over here, the hot flue gases are on the outside and cold flue gases in the center. Same thing happening over here, Whereas this is what we come up with, that the hot flue gases are still in the center, cold flue gases outside. Same thing at even 20 foot elevation. So very different heat transfer profile with inclined firing. We got much more uniform heat transfer profile. We did it even at 30 feet and 40 feet, and you can see the difference. I mean, I don't have to explain to you, they are all self-evident, we also looked at CO concentration, and typically in the industry, any concentration of more than 2000 ppm or red color is flame. And you can see at 5 foot, the situation is not that bad, but at 10 feet elevation, the situation is very bad. You can see over here. The flames are kind of spreading all around. And whereas in our case, the flames are centered in the furnace. And here at 15 foot, you could see the flames are almost in the tubes, and the core is the cooler. So the flames all around and core is whereas the burner should be there, And you can see the difference, In our case, it is much different actually. We have hot flue gases in the center, the flames are in the center, and cold flue gases, no CO outside. So the flames are kind of restricted, So we did extensive CFD modeling, convinced ourselves, convinced our client to ensure that once we put these burners, high tube metal temperatures will be history. You won't have any issues, So in CFD, typically anything more than 2000 ppm or 2500 degree flame temperature, flue gas temperature is considered as flame. And you can see the existing case where we have these flue gases, the flames impinging on the tubes, and that's where they were having this thing. So it was almost like a cloud into the tubes. And when we did it, you can see everything is in the center, Now flames did become little longer, I would say about 4 or 5 feet, but everything was contained in the center actually. And we also did several models, we looked at the TMT models. What we do is we take the FRNC heater simulation output and put it in our CFD model, fluent model, merge the two or marry the two. And then we see, and here you can see the flux radiant tube metal temperature profile and existing and revamped actually. And I can show you we have almost like 60 degree, 65 degree temperature reduction. Now, in reality, in real life, we got more than 100 degrees reduction in tube metal temperatures. The heater has been operating successfully for last 5 years without a shutdown. No flame impingement has been observed. So this shows you the flux profile in the 3 sections, top 1/3, middle 1/3, and bottom 1/3. And you can see we were able to reduce the bottom flux from 20,000 to 15,000 and increase the middle 1/3 from 11,000 to 17,000. So we made it a lot more uniform as compared to what they had before. And the overall heat flux still remained the same. So there was no reduction in heat transfer in the radiant section. I just want to tell you once again. So in summary, there are several benefits of inclined firing: significant reduction in tube metal temperatures, low coking rates, higher tube life and run length. You don't have any flame impingement. You don't have any hot spots. In most of the cases, we are able to increase the capacity also, and uniform firing achieved across the tube. So uniform heat transfer is possible through inclined firing. This picture is from our first installation at Delek. You can see the ultra low NOx burners in an inclined fashion. This is just to give you a little history of our references. The first 2 heaters, we installed it in 2010. Then later on, we installed it at a very large crude heater at Citco Corpus Christi, which was having tube failures. We installed this in 2012. We have installed it in HPCL Mumbai in 6 heaters, and they have been working very nicely. We installed it in Countrymark DHT charge heater, and when we did that, we increased the capacity of that heater by 60%. We did a new hot oil heater for Gladio with 6 burners at an angle. Valero is the one which we presented you the case study today. Then we did another project at Sasol. This was a brand new heater where we put 12 burners in an inclined firing. That heater has started. And all these projects have been working very, very successfully. And I just want to let you know that this is a very simple concept. We want to show, that's what we wanted to show it to you today. We are very confident if you use this technology, you will get rid of hotspots and flame impingement. You will be able to extend the life of tubes. You will have a very good performance. So if you have a heater which is facing issues, it could be any heater, it could be coker, cracking, crude. We would like to evaluate and let you know whether inclined firing is a viable option. Well, thank you very much for giving me a patient hearing. I am very sure that you must have learned a few things today. Please send your questions and I'll be more than happy to answer these questions for you. So I have a few questions over here. The first one is, can we go for inclined firing for both fuel oil and fuel gas burners? Yes, you can do that. I don't see any problem. Can we fire both fuel oil and fuel gas burner together in the same burner block? You can do it. Normally, it is not recommended actually, but typically you can do it. I mean, if you're currently doing fuel oil, fuel gas firing in your existing heaters or existing burners, you can continue to do that. We don't see any problem. HPCL burners had combination firing. I just want to let you know that HPCL burners were combination burners. What will be the percentage of free radiation duty of the total heat absorbed in the radiant section? Generally about 70-30. So 70% or 75% of the heat is absorbed by direct radiation and 30% by re-radiation. That's basically the typical number between the direct radiation and radiation. What is the effect on NOx emissions? Did you see any increase after installing inclined burners? Good question. No, there is no effect on increase on NOx. If NOx would increase, no refiner in US would let me install these burners. So we, when we installed it in Citgo, we installed it in Valero, any project, we made sure that the NOx emissions were within the limit. So no NOx increase, we will guarantee that. Wouldn't inclined firing burners create problems with air and draft control? No, it won't create any problems. You will still be able to control the combustion air and draft like what you were doing before. So we don't think that that should be a problem. What was the increase in cycle length between the heat tube decoking for coking furnaces? I mean, I would say it will go almost like from 6 months to 2 years. That's typically what I would tell you. Is inclined firing technology applicable to combustion combination fired fuel gas fuel oil burners? Yes. Do you supply burners? Yes, we supply burners. I mean, that's basically, I think we can help you by specifying the burners correctly. Have you installed inclined burners in a down-fired reformer? We did a study for one installation, and typically in the end walls where you have the 50 or 60% burners, those are the rows where we can install the burners in an incline. Can the inclined burners be pulled out for cleaning while in operation? Yes. It's almost, these burners are almost in the same manner as vertical burners. So there is no difference. You won't even see the difference of 5 to 7 degree angle, you know. So you can pull them out for cleaning, you can take them out for maintenance. We don't see any issue there. What are the maintenance requirements for inclined burners? Still the same. It's not any different. What about the impact on bridge wall temperature? No effect on bridge wall temperature. I showed you the flux remained the same. It did not change. Good question, actually. So the flux remained the same, and we have done this in several heaters. And basically, as I said, the flames do not come into the picture when we are doing the radiation heat transfer, you know. What could be issues for inclined fired coker heaters if inclined towards the refractory and heats it? So we make sure that your refractory is able to withstand these flames, and also these ultra low NOx flames are much cooler flames as compared to the standard burners. So we don't see any issue, you know. It can be done without any major modifications, you know. How about the effect of emissions for the same type of burners? No effect on the NOx. Otherwise, we won't be in business or installing this in so many heaters. We make sure that your NOx emissions are never, you know. So would you need to install redesigned burners to address different flue gas patterns? No, actually, I can reuse your existing burners also. I mean, in Citco, that big crude heater, they said we don't want to go for new burners because of the permit issues. Why don't you use the existing burners? And I use the existing burners. So I can use your existing burners and put them at an angle without any issues, some cases where we see that if the burners are not sized correctly or designed correctly, or we see a specific uh, reason for changing, so we change it actually. But we can use your existing burners. Do we have to change the refractory to BICS if the flames of burners are impinging? I think it will have to be very, very specific. We will have to look at the refractory. My guess is most of the refractory we put in these heaters are designed for 2300, 2400 degrees F. So we don't see any problem in the refractory. However, it will have to be checked. Yeah. Can we go for alternate or at random fuel oil fuel gas firing? I don't see any problem there. I mean, if you want to use, if you talk to burner vendors, they will recommend that why don't you fire oil in one burner and gas in another burner. They generally don't recommend you to fire both fuels, so you are good actually. I mean, to continue doing whatever you're doing. What are the changes to the floor? Very little actually. We normally take a portion of the floor, which is to be replaced in most of the time. So we take that portion of the floor, prefabricate a new floor, inclined floor, and put these burners, prefabricated. In one case, we even did not change the floor. We just added one very small portion, So the floor changes are very, very minimal actually. What will be the time required for modifications? We have 14 burner blocks per heater zone with 55 giga. Most of the time, I think 2 to 3 weeks is typically the turnaround time for most of the jobs. The good news today is that we can prefabricate everything in the shop, bring it in modules, and then just change the floor plate or change the burners, adapter kit. So it can be done very, very fast actually. The ceramic fiber refractory cannot withstand flame impingement. Yes, you're right, Halim. I mean, it can be done. But you have to put something, which can withstand or do some other modification. We will post the webinar on our website, and also and you will get a link for the recording, so you will have the presentation. Well, thank you all for giving me this opportunity to present high tube metal temperatures issues and how it can be solved by inclined firing. If you have any heater, we will be more than happy to look it over and get back to you with our recommendations. Thank you again. Have a nice day. Bye.